Hello, I'm Gil Shohei, and I'm a member of the Space Environment and Satellite Systems Lab at Stanford University. Today I'll be talking about my research into dusty plasma effects in hypervelocity impacts. Hypervelocity impacts routinely occur in space due to meteoroids and orbital debris impacting spacecraft and small solar system bodies. These impacts occur at velocities between a few and tens of kilometers per second and are termed hypervelocity because they occur at speeds greater than the speeds of sound in the materials, resulting in hydrodynamic behavior. The risk of mechanical damage from large impactors is obvious, and these can result in catastrophic damage if a critical component is hit. For example, we can see this image of a solar panel from the Hubble Space Telescope, where we see a large hole and cracking in the surrounding area. Large impacts are rare, however, and the flux of microscopic particles that are too small to cause mechanical damage is orders of magnitude greater. These impacts still pose a threat to spacecraft electronics, because the impact-generated plasma can produce electromagnetic emissions in the form of a broadband EMP and radio frequency radiation, and these can be harmful to spacecraft electronics. We consider an impact where a hypervelocity projectile hits some target material. On impact, kinetic energy is converted to internal and thermal energy, and a crater starts to form. At this stage, we have a dense plasma in the warm dense matter state and observe high-velocity jetting at a low angle relative to the horizontal. As the plasma and neutral vapor and condensed phase material, which I'll refer to as dust going forward, expand into the vacuum, electrons can attach to the condensed phase, potentially forming a dusty plasma. We also see electromagnetic emission at this stage, depending on impact conditions. As the plasma, gases, and debris continue to expand into the vacuum, charge separation can occur because the initially jetted plasma follows a different trajectory from the plasma and condensed phase material ejected later on. This can lead to long-range electromagnetic fields. The effect of dust charging on the impact plasma, RF emissions, and threat to spacecraft, however, is poorly understood. My research aims to address three major questions. First, what are the characteristics of the ejected material? We can't assess how much dust charging occurs without knowing what's ejected on impact. Second, how do we model the evolution and charging of impact debris over the many orders of magnitude and density spanned by the expanding plasma? And finally, how does dust charging affect the plasma expansion and associated observations? This is a first step towards understanding the impact of dusty plasma effects on the threat to spacecraft. To address the first question, we conducted a light gas gun impact campaign in early 2019 at the NASA Ames Vertical Gun Range, which is a two-stage light gas gun facility which shoots projectiles vertically at approximately 5 kilometers per second into a 2.5 meter diameter impact chamber. The chamber is evacuated to a low vacuum with a 0.5 torr, or about 1/1000th of an atmosphere neutral background, which we will look at the effect of later on. We shot 13 targets of various materials with 6 milligram or 1.6 millimeter diameter aluminum projectiles. I'll focus on impacts on aluminum and powdered regolith simulant targets as analogs for spacecraft and small solar system bodies, respectively. The instrumentation included a variety of sensors, including optical instruments such as high-speed cameras, RF antennas, and Faraday cup plasma sensors, which were co-located with witness plates, which I designed for measuring the impact debris. These witness plates consist of a thin film membrane made from mylar or PET film, and the results that I present are from the 1 micron thick films, which have the best mapping from punctures due to secondary debris impacts to the size of the impacting debris. And I analyze those witness plates by counting holes under a microscope. So looking at the high-speed video from impacts on aluminum and powdered regolith targets, I first want to point out the very different timescales of the impacts. While the impact flash from the aluminum target lasts only about 20 microseconds, the regolith target continues to eject material for well over 100 microseconds. Pausing the video where the debris plume is visible, we can also see that they have very different structures. The regolith debris are ejected in a vertical cone with approximately a 20-degree half angle, while aluminum debris are concentrated in a thin conical sheet located about 30 degrees from the vertical. Examining the craters, where I've placed a representative projectile in the aluminum crater for reference, we can see that the regolith target produces a crater about 10 times larger than that in the aluminum target. It also ejects about 400 times the material by mass. This is unsurprising given that we're comparing a solid metal target with a granular medium. Note, however, that the debris from the aluminum impact are concentrated in a narrower region of space. This plot shows the solid angle normalized cumulative distribution of microscopic impact debris from these two target materials. The right axis shows the expected number of impacts by particles 1 micron or larger to the plasma sensors. And the shaded region shows the 1 sigma uncertainty band based on uncertainty quantification on the measurement, hole identification, and uncertainties due to small number statistics. Microscopic debris from the regolith analog follow a power law with an exponent of about 1.7, while the debris from aluminum targets follow a power law with an exponent of about 1.2. And while there's very limited existing data on impacts on aluminum targets, our results diverge significantly from extrapolations based on macroscopic debris measurements, and patching the transition from the behavior of microscopic debris to macroscopic debris is an area of future work. I also did wavelet transforms of the plasma sensor data in the debris plume, and these are normalized by the largest value per shot to make the scale consistent. Dust impacts occur at a timescale that's faster than the plasma sensor response and show up as thin bands in the data, and the number of thin bands corresponding to impulsive measurements agrees in order of magnitude with the predicted dust flux from the particle size distribution. I'll now go on to the dust charging model. We consider a dust particle with a given radius, surface potential, charge, temperature, mass, and velocity vector, which in theory may not be aligned with the expanding plasma. And the effect of gravity is negligible, but depending on ambient conditions, the dust may interact with a neutral background. For example, due to the partial vacuum at AVGR or water vapor around an outgassing comet. To complicate things even more, if the surface temperature is high enough, the dust may emit electrons via thermionic emissions and ablate neutrals from the surface. This is a complicated picture, and we want a simplified model to rapidly assess dust charging and evolution in the impact environment. To make things tractable, I turn to orbital motion limited theory, which assumes dust particles come from infinity and conserve angular momentum and energy. I extended the OML model to account for effects such as large dust, thermionic emission, and other physical terms that may be relevant in the impact environment. The current balance includes collection of ambient plasma particles and thermionically emitted electrons from the surface. The force balance includes direct momentum transfer from collected particles, Coulomb drag due to scattered particles which don't reach the surface but interact electrostatically with the dust, and forces due to external fields. The energy balance includes kinetic energy transfer from collected particles, recombination and thermalization at the surface, energy loss to thermionic electrons, and thermal radiation and ablation. And finally, the mass balance includes accumulation of like particles and ablation of neutrals from the surface if the surface temperature is high enough. This is still a complicated picture with many parameters, and I tried to simplify things by parameterizing as much as possible using fundamental quantities. I normalized velocities by the thermal speed, mass by the electron mass, temperature by the electron temperature, length scales by the screening length, and the surface potential by the electron temperature in EV, for example. Dust charging occurs at a much faster time scale than other phenomena, and we can assume the surface potential and charge are in quasi-equilibrium at any point in time. We can then solve for the equilibrium value as a function of these parameters by imposing current balance and root finding. We then evolve other quantities, such as the position, velocity, temperature, and mass of the dust particles using a system of coupled ordinary differential equations. Closing the system requires a model for the environment as an input to the dust charging model. To avoid the need for computationally intensive hydrodynamic simulations, I derived a renormalization group symmetry model for an expanding plasma bunch. This gives a self-similar solution to the collisionless Vlasov equation and gives us the velocity distribution as a function of space and time. Taking moments of the distribution function gives the plasma density, expansion velocity, and other quantities. Closing the system requires a model for the charge generated on impact and for impact cratering, and we use those as an input to set the initial conditions of the plasma expansion. Comparing with actual plasma observations, we can see that the predicted current from the renormalization group model agrees reasonably well in terms of the arrival time and the signal duration for impacts on aluminum targets, assuming reasonable inputs to the model. These currents shown on the plot are normalized by the peak value observed in each shot so that they show up easily on a single axis. And although the model makes many assumptions, the predicted plasma densities are in good agreement with experimental observations and simulation data. I also want to point out that we observe mainly negative charges from the aluminum impacts, but we see positively charged debris in the impact on the regolith target. I'll now show some of the major results that are computed using the experimental data combined with the dust charging model and the expansion model. First, I estimated the total charge attachment after impact by integrating the predicted surface charge over the observed particle size distribution. The shaded regions show 1 sigma error bars accounting for uncertainty in the measured particle size distribution and in the charge production model. We predict a small fraction of the electrons that are produced initially attached to dust in the first microseconds after impact. However, we have to note that debris are concentrated in a narrow region of space and interact with only a fraction of the impact plasma. So charge depletion will be much greater in the debris plume. And given that a couple % of charge attachment is enough to have significant effect, this suggests that localized dusty plasma effects are likely in the debris plume. We next look at the effect of the ambient environment, comparing complete vacuum and outgassing comet and the partial vacuum at AVGR. The neutral density around a comet is too low to appreciably affect things, and the results from a comet are indistinguishable from the complete vacuum. However, the neutral background at AVGR has a significant effect on the predicted trajectories and surface charge and potential. First, we notice that drag due to the neutral background is sufficient to significantly decelerate or even stop debris, and stopping is indicated by an X on this plot. The neutral background also leads to a less negative, more positive, or even the potential changing signs from negative to positive, depending on the dust size and ejection conditions. And this is because collisions with the stationary neutral background generate a heat flux that partially counteracts radiative cooling, which is the dominant energy flux after the first 20 to 100 microseconds after impact. The ambient neutral background also raises the boiling point because of a higher background pressure, and this results in less ablation and less ablative cooling on hot particles. The net result is a predicted increase of only about 20 to 100 Kelvin in the surface temperature, but because of the functional form of the fermionic emission current, which includes a square times this exponential, this leads to a significant increase in fermionic emission and a significant change in the predicted charge and surface potential. Finally, to compare with experimental results, I integrated many trajectories equivalent to the expected flux to a plasma sensor after 50 shots. And this allows me to qualitatively compare with observations and account for the many uncertainties that we have both in the initial conditions, the particle size distribution, and other factors. This plot shows the arrival time and surface charge of each of these integrated particles. And we sample the size of each particle from measured particle size distribution, including uncertainties. We sample the initial velocity based on observations and experimental data, and the ejection temperature based on a heating model accounting for interactions with the dense plasma initially after impact. The current shown is an expectation value based on averaging over all the simulated trajectories. In reality, we observe an impulse train from the dust impacts, but this gives us a qualitative prediction of the sign and quantity of charge deposited. The predicted arrival times agree reasonably well with plasma measurements, and we can see that we're predicting a predominantly negative current to the aluminum sensor and a positive current to the negative sensor, which agrees with observations. So to summarize, this work is the first attempt to study dusty plasma effects in hypervelocity impacts. I measured the particle size distribution of microscopic debris from aluminum and regolith simulant targets and found that the distributions follow power laws. I also developed a dust charging and evolution model based on orbital motion limited theory with modifications to ensure that the model is reasonably valid throughout the expansion. Finally, I combined the experimental measurements and the dust charging model, including measurement and model uncertainties, to assess the effect of dust charging in the impact environment. I found that dusty plasma effects are likely to occur in the debris plume shortly after impact. I also showed that the impact environment significantly affects debris evolution and that we need to account for the effect of the partial vacuum at AVGR when extrapolating to space-based impacts. I also identified thermionic emission as the most likely mechanism for observations of positively charged dust in impact experiments. And this is a first step towards understanding how dusty plasma effects and hypervelocity impacts affect the threat to spacecraft electronics posed by the impact plasma. So to conclude, and before I wrap up, I'd like to briefly thank everyone who made this PhD possible, including my advisor, my lab, and especially the DOE Stewardship Science Graduate Fellowship, which gave me the opportunity to really focus my research on the interesting science questions, and also to do a really exciting practicum at Sandia National Lab in late 2018. Thank you.